was born at the end of the 1960s, right at the tail of the end of the decade, but Neil Armstrong hadn't yet walked on the moon, but the decade was almost finished. I was therefore a child of the 70s and 80s, and like all children of that era, I raced around on my rally chopper bike, I played with action figures, and I built Lego. I was really into comics, both the asinine humour of the Beano and the Beezer to my hero Roy of the Rovers, and my interest in science fiction, 2000 AD, the home of Judge Dredd. It was a golden era for science fiction, all the way from fantasy set in space like Star Wars through to dystopian future visions like Planet of the Apes, Logan's Run and Rollerball. And these were fueled by visions of the future, constantly being forced upon us by things like Tomorrow's World, the tech of the future, the things that would make our lives easier and greater in the future to come. Probably the film that was heralded the greatest for this was Blade Runner, Ridley Scott's image of Philip K. Dick's 1950s novel, set in a near future with lots of predictions about the future that people generally thought were good science fiction workings of what might happen. And what did it predict? Well, it predicted large global-sized cities that were so heavily polluted that constantly seeding rainfall. Well, we're not quite there yet, but with global climate change, this is becoming a threat. It predicted a mishmash of cultures, a common language between Hispanic, Chinese, English. We're not really there yet. We have global communications and language, but we're not quite there to that full cultural melting pot that was predicted. It predicted flying cars. All the way since I was a child, we have always predicted flying cars. Well, we're not really there. We have the technology for this, but I can't commercially go out and buy a flying car. It predicted replicant humans, artificial human beings. Well, biotechnology is immensely powerful and has come on in the last 100 years immeasurably, but we still can't create artificial human life. It predicted enormous advertising hoardings of the size of buildings. We are getting somewhere with this. This is a picture of Queen Street in Cardiff, and the curved picture you see of Gareth Bale is a moving image, is a moving picture display screen. And in a very unheralded scene in Blade Runner, where Rick Deckard, the main protagonist, speaks to his love interest Rachel at a video phone at the side of the street, where he goes into a booth and can see her face as he talks to her. This was revolutionary in the 80s. And yet I now have this. I can talk to somebody the other side of a planet while I sit under a tree on a hill, on a small mobile communication device. Let's face it, even in Star Trek, where we had faster than light travel, we had beaming human beings from a spaceship down to a planet, they would still talk to the spaceship by a radio that goes beep. This communication device, this telephone we now have, is immensely powerful and way beyond where we thought we would be in the future. So how did we get here? Well, it started with a load of black and white men. A load of men at the turn of the century that developed an understanding of nature through observations and postulates by, for instance here, Prince Louis de Broglie and Max Planck, who were explaining experiments by Compton and Thomson. And through a lot of effort by a significant amount of physicists worldwide, we gained an understanding of nature that seemed incredible, preposterous even. And we developed a theory called quantum mechanics. This developed into a quantum theory of solids, which have enabled us to understand the behaviour of matter like we have never done before. When you come to university, you'll learn this in your second year. This is where you start learning quantum mechanics and applying that quantum mechanics to our understanding of the state of matter, condensed matter physics. I'm just going to skip forward to 1947. Why 1947? Well, if I do a quick Google search, I can reveal that India and Pakistan became separate nations, for example. And as I reveal each one of these significant things that Google I think the Dunlop inventing the first rubber tyre is very soon. However, down right at the bottom of the list, you might find an innocuous comment about the invention of the transistor. Let me put this into some priority list for our modern day life. This is the most important invention that's happened in the last 100 years and has transformed our modern life. These are the three guys that invented this device. They worked at AT&T Bell Labs. They weren't university people, they were company men from in the 1940s, 1950s. What did they invent? Well, this is a picture of their miraculous device. It doesn't look much, but this is a germanium-based transistor, a 3-terminal switch that replaced valve technology. And what high technology were they trying to work on to replace? Well, actually, they were trying to miniaturize the hearing aid. They were trying to make the hearing aid smaller. And for that, they knew they had to get rid of valves and they had to replace it with something that worked a bit like a valve. You see, hearing aids were very big at the time and they wanted to shrink it to the size of something that would fit on somebody's head. Incidentally, as an aside, we all know who this guy is. This is Albert Einstein. Actually played a role in early quantum mechanics. What people don't know is this is the number of Nobel Prizes he won in physics. This is John Bardeen. This is the number of Nobel Prizes in physics he won. So he's the only physicist to have won the Nobel Prize for physics twice. A scientist that very many people haven't heard of and a true genius. Let's skip forward to the present day. Let's remind ourselves where this has come. The global electronics market now is one of the biggest physics-born businesses on the planet, bar none. And what does it fuel? It fuels our everyday life, all the way from gadgets through to essentials, through to life-saving critical medical diagnostics. Without computing, without processing, without electronics, all these things would not be possible. Even modern day cars would probably fall off the road if it wasn't for the electronics keeping them on. And let's not think it's just gadgets. Global climate change is one of the biggest problems we face. And yet semiconductor technology and electronics technology has a major role to play in renewable energies. For instance, power conversion in windmills, in terms of efficient use of fossil fuels. The solar industry is all to do with semiconductors. Photovoltaic cells are semiconductor devices. So I keep talking about semiconductors, and we mentioned that this was a germanium transistor. So why is it that the majority of our technology is silicon? Well, silicon can be made industrially very easily. It has a wonderful advantage in a native oxide that sits on the surface. And this enables us to turn this simple transistor idea into a technology. This is a side-on view of a CMOS transistor device made in silicon. It looks a bit complicated, but essentially it's a hose pipe with an input for electricity, an outflow of electricity, and some way of stopping the flow of that electricity. My 3-terminal switch. This is how a physicist and an engineer might view these devices. The left-hand side being the engineer's view of a circuit diagram, the right-hand side being the physical makeup of the device. But essentially, they're the same thing. This has gone on to lead to our current day modern processors using complementary metal oxide semiconductor technology, or CMOS. And we have a phenomenal technology now. Our latest transistors are so small that we can fit thousands, millions around the circumference of a human hair. Devices are tremendously small. You'll learn about this in your 3rd year. Courses on semiconductor devices and applications cover the groundwork of the devices that came out of that 1950s breakthrough. What was it powered by? Well, this is Gordon Moore. Gordon Moore was one of the founders of Intel, worked for Fairchild Electronics, and in desperation, going to a conference, not really having much to talk about, realised that the number of devices on a chip was roughly doubling every 18 months to 2 years. This was coined as Moore's Law, and in those days they didn't have a phenomenal amount of data, but it seemed to be a linear trend. Flip forward 50 years, and this has driven the silicon industry to year on year produce more powerful and faster chips with smaller and smaller devices. And that inherently becomes a problem, because our devices are now getting to the sorts of levels where quantum effects are starting to mess up the operation of the device. A wonderful playground for physicists, but a pain for electrical engineers. Let's remind ourselves what some of the things that processing has enabled us to do. We all know that we use computers in everyday life, but what we don't think about is that actually this has fueled a lot of creative arts. From the gaming industry, which is a significant industry for the UK, all the way through to things like special effects and the film industry. These are immensely enhanced by digital imagery nowadays. And so the whole of this industry has been transformed by the power of processing. But then that power of processing and those techniques in imaging and special effects and games can also be used for good. They can be used in medical imaging. Medical imaging borrows a lot of the imaging technology from game industry to visualize and diagnose. So, what can't silicon do? Silicon is in all our processors. Silicon is in all of our workhorse memory devices. But there are things that silicon can't do. Well, there are two main things, really. Silicon can't emit light. It can't emit light efficiently. It can absorb it. We have silicon solar cells, but it can't easily emit light. It can't work really fast. And by really fast, I mean really fast. Okay, it can't handle extremes of power, so I'm going to say there's three things. Okay, there's four things. It's not a particularly great playground for researchers. Well, what might be used as an alternative? Well, we can take elements from group 3 and group 5 of the periodic table and we can combine them. We can combine them into the compound semiconductors, things that have not dissimilar properties to silicon, but enhanced properties for other attributes. So materials like gallium and arsenic combine to make gallium arsenide, indium and phosphorus to make indium phosphide. We can take a range of these compound semiconductors. This is a picture of the whole family of the compound semiconductors with their interatomic spacing, their lattice constant, and their band gap energy, a significant characteristic in semiconductor devices. And that band gap roughly controls the light emission from the semiconductor. Here you can see that this spans all the way from almost the ultraviolet to the infrared for compound semiconductors. What does that make? Light emitters, light emitting devices, light emitting diodes and lasers. We know that the lighting revolution has already happened, and now LEDs power all the lights in our homes and displays. Right from the 1970s, where we just had red LEDs on Texas calculators, we now have pretty much every colour in the rainbow. From material science and quantum engineering, we have now achieved the whole spectrum of light-emitting devices. You'll learn about this in your third year in laser physics and nonlinear optics. And what's important about optics and semiconductors? Well, of course, optical fibres drive the internet. You need a laser at one end of an optical fibre transmitting your photon and a detector at the other end. Even if you're not on superfast broadband, at some point your signal will be transmitted by photons and light. Remember the bad old days when we had satellite communication delay? Have you ever thought about the fact that we speak to people in America with almost no delay whatsoever on the signal? It's a video image at the speed of light. High-speed electronics, silicon isn't so great at doing. And when I say high-speed electronics, I mean ultra-high speed. Things that enable us to have high-bandwidth video signals Mobile communications, Wi-Fi, are all driven by compound semiconductors. Modern day communication technology would not be possible without this range of semiconductor devices and materials, from silicon to processors, silicon in memory to compound semiconductor communication chips. It's also a magnificent playground for quantum electronics, investigating quantum mechanics from first principles and fundamental study using semiconductor device technology. You'll learn about this when you get to your final years at university, where you're looking at the forefront of research in device technology. Cardiff is exploiting this. We have an institute for compound semiconductors. We are coupled with industry to try and embed industrial practices into research to make compound semiconductors relevant for industries quicker to exploit new technologies. So to summarise this podcast, what have I said? Well, what will you remember from this podcast? You might remember some odd words. You might remember semiconductors. You might remember internet and maybe transistors. I hope you remember transistors. What we really will remember, hopefully, is revolution. Revolution that has brought about a communication revolution. From 100 years ago, when scientists were doing fundamental work in our understanding of matter, to 100 years later, where we are now video phoning people across the globe. We are way ahead of where we predicted the future would be. Our job at Cardiff University is to train and inspire people to become semiconductor scientists and engineers and create the next revolution.